All right, so previously we talked about the instrument and we started talking a little bit about the theory that goes along with the instrument, and we said that this really is important in quantitative work and it uses UV and visible to do the quantitative work. And UV and visible have now been assigned wavelengths. And now we know what the definition of a wavelength is. So, for instance, here we go. This is a picture of a prettier wave than what I drew in the previous video on the notes. But this gives you a description of the definition of the wavelength. So again, it goes from crest to crest, which is the top of the mountains. If I measure that length from the top of one wave to the top of the other wave or the other crest, that wavelength is assigned a number. If that number falls between 2 to 400, that number is classified as UV. If that number goes between 4 to 900, that's kind of where we put our cutoff, that is classified as visible. And again, keep in mind that these numbers are rounded and they're cut clean, meaning UV really does go below 200. We're rounding it off 200 for convenience. And visible, there's a gray area in visible as well. Some people say 800, some people say 900, some people say 1100, but that gray area we just kind of chop off. And the reason that we do that is because this is what makes practical sense in a laboratory. Most of the time when I'm running visible analysis, I don't go above 900. Most of the time when I run UV analysis, I don't go below 200. This is just the working natural ranges of compounds that we see in a lab. So, depending on the textbook, if you begin to look this up through Wikipedia, you might see different numbers, but again, for our purposes, we're rounding off and we're making it simple. So, we said that this wavelength can change, and this wavelength can change, and these waves can hit me quicker or slower. If the wavelengths are hitting me quicker, they're more energy. If they're hitting me slower, they're lower energy. So here is a slide that maybe shows that again a little bit better than the awful mess that I drew in the previous video. But here we see waves that are happening over and over and over, and I can measure that wavelength if I wanted. And this wave is coming to me more often. So this is a higher energy wave. And this wave is coming to me quicker and quicker and quicker. So again, that has more energy than that one and that one. And finally, this one, this is really coming to the boxing match, and it really means some business, and I want to stay away from it because this is going to punch me hard, and it's going to punch me quick, and I won't even have time to breathe in between the punches. These waves are coming to me so fast. And because of that, this has the highest energy out of all four of these examples. So, wavelengths and energy are inversely proportionate to each other. Shorter wavelengths are higher energy, right? Just like we saw with UV and visible. This had a shorter wavelength. The punch is coming to me quicker. Therefore, the energy for UV is much higher. So as the wavelength goes down, the energy goes up. So, on a test, some of the questions that you might see would be this kind of relationship. Here are four choices of wavelengths. Which one has the highest energy? Here is UV and visible. Which group has higher energy? What is the definition of wavelength? What is the abbreviation that we use for wavelength? What range do we use for UV? And what range do we use for visible? Those might be some of the test questions that you'll see. So again, it's very important that you watch these videos. It's very important that you take this process seriously, Not only so you can understand what's happening in the laboratory and the instrument, but so that you can do well on the testing portion as well. Okay, so there's the picture of different waves. Notice though that this is not using lambda, right? Lambda, we said wavelength is typically provided in the unit of nanometer, but this is not a nanometer. This is Hz. Hz is something that we call a hertz. Okay, so let's define that for a minute. Hz is called a hertz. That is the unit for what we call frequency. Frequency is how frequent the waves are hitting me. That's the proper term that we're giving this. So UV has higher frequency than visible does. Visible has lower frequency because the punches are coming to me slower. Visible has high frequency because the punches are coming to me quicker. Well, frequency is what we term that. So frequency and wavelength are related, right? Frequency is provided in terms of hertz. We have to have a proper definition of what frequency really means. And it's basically how many waves do I see in 1 second of time. So I give the wave 1 second to throw as many punches as it can. In that 1 second, if it throws a lot of punches, that means it has a high frequency. I'm getting hit more frequently with the wave. In that 1 second, if the wave is kind of slow and it doesn't punch me a lot, then it has a low frequency. I don't get those punches and I don't really get bruised from the fight. It makes me happy. So that is the definition of frequency, and that's what it means. How many waves or how many punches am I getting in a 1 second time interval? I'm only going to give it 1 second, and it can throw as many punches as it wants to during that 1 second, but that is what we call frequency. So again, frequency and wavelength is related, but there's a difference here. If the compound has high frequency, frequency also has an abbreviation. It is kind of a cursive V with a long stem on it, kind of like that. So this is frequency. If it has a high frequency, then that means it has a high energy. So frequency and energy are directly proportionate to each other. High frequency, high energy. Low frequency, low energy. That is unlike wavelength. Wavelength is indirectly proportionate. Lower wavelength, high energy. So this is something that people typically have a very hard time distinguishing between. But that's the way that I want you to think about it. Think of frequency as number of punches. More punches, more energy. Think of wavelength as this time period in a way. I know we're getting kind of confused now, but think of wavelength as how long it takes the punch to happen. So the wavelengths, if they're large, means it takes a very large amount of time for the molecule to reach back and hit me. Okay? So that's the difference between wavelength and frequency and how it relates to energy. Okay. So that's where we'll stop with this video. I think that's enough. That gives you some more terminology and some more definitions before we go any further. And in the next series of videos, we'll pick up and talk about the definition of types of samples that are well suited for the instrument.